So in type 1 superconductors, we have the intermediate state, which is shape dependent, in which we have large domains of normal state and superconducting state. So this is the characteristics of type 1 superconductors when we do apply a large enough field. Let's go now to the other case in which coherence length is smaller than penetration depth. We have the same magnetic flux density, and now it grows, it drops to 0 on a scale lambda, which is like this, and the number of spin electrons drops to 0 on a scale psi, which is like this. So in this case, you see that psi is smaller than lambda, and the shape of those two, so we have the magnetic contribution, positively charged superconductor, we have the electron ordering contribution or condensation energy, which goes like this. So this is much sharper, and now if we add these two, we see that we have here a minimum free energy. What does it mean? It means now the system would love to have as much as possible of interfaces, surfaces. How can you do that? Think of a very, very thick cylinder, which a given volume. That would be type 1. If you want to keep that volume, but to increase the interface between the normal and the superconductor, you will do what? You will split that one in 2, in 4, in 8, and so on until you get a large number of very thin cylinders. Now the total surface is much larger than in the first case. So this is the type 2 superconductor in which the flux lines want to maximize the surface energy. So this is called the mixed state, and these are the type 2 materials. Okay, how is this mixed state? So we discussed about we can make maximum possible of the surface between normal and superconducting regions. So we decided that the best way is to have many cylinders. So these are those many cylinders. What we have there? We said that we need some vortex, some normal phase. So we have the cores of the vortices, which are made of regions of normal material. What we also have, we have to sustain that magnetic field which is inside. How can you sustain a magnetic field? Well, in type 1, we can sustain a magnetic field by circulating currents outside the whole superconductor. Here, we have to create superconducting currents which have to circulate in the superconducting region here and to create magnetic flux line. So a vortex is composed of a normal core, usually of cylindrical shape, and a circulating supercurrent, which creates one flux quanta. We will see later why this flux quantization has to happen. Now, because we do have there interaction between currents and interaction between the flux lines, it happens that in a very, very clean superconductor, the cores arrange in regular pattern to minimize the repulsion between cores. And this one is the closed packed hexagonal lattice, which is for flux lattice. It is quite interesting that so these are called Abrikosov vortices. I don't know if you know much about Abrikosov. Abrikosov was a student of Gisborne, and he played just with theory. At that time, there was no experimental evidence of something else than type 1 superconductors. So he was just a theoretician, and he played with something like, okay, let's see what happens if coherence length is smaller than penetration depth. that was something which nobody thought about because there was no material that things there then. And he just played with equations and so on, and he find the only solution, some singularities. Well, okay, that singularities is vortices. And he continued to make the calculations, but he did a small mistake in numerical calculation, and when he first published, he said that the minimum energy will have a square lattice. So he missed something like 2% of the calculations, but so from the original work of Abrikosov, later on somebody calculated again and said, no, should be a triangular, or let's call it closed hexagonal lattice. So the first paper of Abrikosov is saying that the vortices will arrange in a square lattice. In fact, there are some special cases of square materials these days in which actually they do align in a square lattice, but this is something not for our talk today. Now that we still have enough time, I want to tell you another story about Abrikosov. Well, Abrikosov moved to US after the collapse of the Soviet Union. His old professor Ginsburg remained in Russia. You know that several years ago they both received Nobel Prize. Probably, I think, together with
Randall.
No, Randall was there a long time ago.
Three different guys.
Anyway, yeah. Doesn't matter. Anyway, so they have received the same amount of money. In Russia, this kind of prizes, they are by law tax-free. In US, it's not the case. So Abrikosov was very, very upset that in the end Ginsburg remained with much more money in his pocket after taxes. This is an actual image, a bit of decoration image of hexagonal lattice. You see how they are packed. You know what bit of decoration is, yes? Well, you have in a low vacuum, you have deposit very, very fine ferromagnetic powders on a superconducting surface with applied field, and that small ferromagnetic particles, they are attracted to the magnetic field, they stay there. And then you freeze the image and look at the microscope. This is a bit of decoration image, how it looks like. Now, about magnetic flux quantization, if we have a ring and we are at a high temperature larger than Tc, we apply a field, then we pull it down below Tc, and then switch off the external field. What happens? It happens that we remain with a circulating supercurrent, and it was proven both theoretically and experimentally that the magnetic flux created by the circulating supercurrent has to be an integer of the magnetic flux quanta, which has this value flux quanta divided twice electron carrier, which is 2 times 10 to the minus 15 Weber. So this is called the flux quanta. So what we have, if we look at that arrangement of vortices, and we draw a line, and we look at the density of superconducting carriers as function of distance on this line, we have maximum concentration between vortices in the core drops to 0. And the dropping to 0 happens on a distance of 2 coherence length. On the same time, if we look at the internal magnetic field has to be 0 in the superconducting region here between vortices, and it has a maximum at the center of the vortex core, and this is how the magnetic the internal magnetic field varies on the distance, and you see the variation is of a distance of 2 lambda, twice the penetration depth. So again, we look here, this is how the field varies inside the vortex and how the density of the superelectrons or the amplitude of the wave function varies inside the vortex. Deep inside the vortex, number of superelectrons density goes to 0, while the magnetic flux is the maximum. Okay, now let's look a little bit of the high temperature superconductors. You have seen the vortex melting line for type 1 superconductors. So what we have here, normal state. We have here the mixed state or the vortex state. And we have here the Meissner state. So in the Meissner state, all the flux is expelled. Between lower critical field and upper critical field, we have the vortex state in which we have that vortex lines, and then normal state in which the magnetic flux is placed here. However, in in high density superconductors for high anisotropy meaning, for example, base systems and so on, we have a much more, let's say, complicated or richer phase diagram. So, for example, if we move from the vortex liquid phase, okay, let's say what is vortex liquid phase and what is the vortex solid. Because we are talking now about high temperature superconductors, in this case we do have quite serious thermal energy because Boltzmann constant times temperature is quite large. So as opposed to the low temperature superconductors in which the difference between the HC2 as function of temperature and the irreversibility field was very, very small. If you one over 1,000 of a Kelvin in high temperature superconductors, because we do have this huge thermal energy, we have a so-called vortex melting line in which the vortex lattice undergoes a first order melting transition, transforming the vortex solid into a vortex liquid. Okay, what is a vortex solid? When you have not very high magnetic field and not very high temperature, if you pass a current and the current is not very high, the deformation is elastic one, comes back. And if you plot current voltage characteristics, you will see probably in my third lecture is at this school, you will have a downward curvature in double logarithmic plot of the current voltage characteristics. And that is the mark of a vortex solid. So vortex solid means the following thing. When you decrease the transport current linearly, the dissipation drops at the power law. So practically you will have very little dissipation if you do not make a very large current. Opposite to that, vortex liquid, if you apply a current, the dissipation will be proportional with that current. So the IV curve will be in log scale a straight line. So in practical meaning, in a superconductor in a vortex liquid phase behaves like a normal material but with a much smaller resistivity. While a vortex solid phase superconductor behaves differently in the sense that the current voltage characteristics are strongly non-linear, favorizing dissipation going abruptly to zero with decreasing applied current. In very anisotropic superconductors, we have some a little bit more complicated, in which we have reentrance of the melting line. So if we are here, we stay at the same temperature, decrease the field, we have vortex liquid, we decrease the field, we go into vortex solid, no dissipation, and then it's a very small region in which with the vortex solid happens something with the elastic coefficients for the deformation, in which we have a very, very narrow region in which we have, again, vortex liquid. So the vortices which are solid here, they melt a little bit here, and then they go into the Weissel state. And this I have proven experimentally by whole flow microscopy some time ago. Okay, so we have seen what vortices are, we have seen what is vortex liquid phase, what is vortex solid phase. Problem is, how can you use superconductors in such a way that we will not have dissipation? You know, if you put a magnetic field and you have a current, you will have a Lorentz force. So, if the field is perpendicular to the current, Lorentz force comes and it is like this, and it is perpendicular to all of them. So, you know the rule of thumb, yeah? So, if you have a force, you will move all the vortices. If the vortices will move, what happens? We have dissipation because the supercurrents will cross at some point the normal course of the moving vortices, and of course they will have dropping voltage. We need to stop them moving. How can we do that? We can do that by creating pinning. So what is pinning? Pinning is a mechanism which locally decrease the free energy of the vortices in such a way that the vortices would like to stay there from the sake of minimizing their free energy. So, pinning forces are actually opposing the Lorentz force, and by doing that, by providing to the vortices some regions of normal material, of having dimensions of same dimension like coherence length, in such a way that the vortex core will stay there and with a gain in the free energy. So what we can have, if we have a defect-free samples, so no defects there, and we have a field like this, and we apply a current perpendicular, then Lorentz force will make all these vortices to move to the right, we have dissipation. Now, if we have some point defect pinning, some regions of non-superconducting materials, which can be inclusions, voids, many types of defects, parts of the vortex are feeling well to stay there. So when you apply a current, the vortices get deformed. During this deformation, you can have dissipation, but dissipation is not that large because the vortex doesn't move the whole of it. And we can have also columnar defects, in which we have column threading the whole material, in which the whole vortex accommodates, and the decrease in free energy is the maximum one. But this type of defects, they are very effective only if the magnetic field is parallel to those defects. Now, what can we have? We have pinning centers which can have certain dimensionality and certain strength. So what can we have? We can have one-dimensional artificial pinning centers, which are linear defects. We can have two-dimensional artificial pinning centers, which are planar defects. And we can have three-dimensional artificial pinning centers, which are the big nanoparticles. Now, if we look at these ones, if they are linear effects, they can trap only one vortex line. If we have this type of